We are going to do another method of computing volume when we're rotating things. So far we've talked about creating or finding volume when we have a solid that is created by creating cross sections or knowing what the cross sections look like. We've talked about how to find volume with the washer method when we're rotating things. And today we're going to learn the shell method, which is still for solids of revolution. Sorry, that's hard to say. So let's look at this example here. So I've got the function graphed, and this is this region here since it's bounded by the x-axis, and we want to rotate this region about the y-axis. Okay, so this looks like one of the problems that we could have done when we were talking about the washer method. And if we were going to do this with the washer method, remember that we said in order to get washers out, to get like circle-like shapes, we need to rotate a line segment that is perpendicular to my line of rotation. So in this case, I would need to rotate a line segment like this. Okay, that seems fine. Except for the problem here is that if I look at that line segment, the right and left-hand side of that line segment is the same function. So we're going to have a problem when we go to find our inner and our outer radius. They're going to look like the same thing, which means that they're going to subtract out and be zero. And we know that this volume should not be zero. So doing this integral in terms of y with horizontal line segments is going to be a problem. So because of how this region is created, we really have to integrate in terms of x. So we're going to need some integral with an x in it. And the problem with that is now these line segments, these doing things in terms of x, are parallel to the line I'm rotating about. So when I rotate that parallel line segment, I am not going to get a washer. Remember, a washer looks something like this. It's a flat little disc. Instead, I'm going to get something that looks like the shell of a cylinder. It's going to kind of be tall and long and have very little width or essentially no width to it. So this is what I'm going to get instead of a washer. We call this a cylindrical shell and usually just abbreviate it by a shell. So we're going to get a cylindrical shell instead of a washer. Okay, and so we have to think about what is the area, the surface area of that cylinder that we get. Okay, and so a few things to take into consideration, remembering how to find the area of a cylinder. So the area of a cylinder in general is 2 pi times the height of the cylinder times the radius. You can recreate that by thinking about cutting the cylinder apart and making it a rectangle. And then you need to know this dimension, which is just the circumference of the circle. The circumference of the circle is the 2 pi r, and then this distance, which is the height. Okay, so that's where that comes from. But this is the area of a cylindrical shell, or the surface area. So now we have to integrate this and figure out what this looks like in terms of our problem. Okay, so the radius of our circle, or of our shell, sorry, is going to be the distance from the line that I'm rotating about, because that's going to be the middle up to the side of one of these shells. So the radius is always going to be the distance from where I'm rotating to one of these little line segments. That's our radius. Okay, so in this case, one of these little arbitrary line segments is an x value. That x value could change, and we're going over to the y-axis, which is where x equals 0. So our radius in this case, which I'm going to usually put first, our radius is going to be x minus 0. We're always doing right minus left. Okay, and then our height is the height of one of these little line segments. In this case, that's just going to be this function because our bottom function is the y-axis. So top minus bottom, we're just going to do top function minus 0. So we're going to get 2x squared minus x cubed. Noticing everything here is in terms of x, so that's good. My bounds should still just be the bounds from the region, the 0 to 2, and we still have the 2 pi out here. Okay, so the way that the shell method works in general, and it's down here, is that we're going to do 2 pi times a radius times a height. And this is, we're going to get this when the little line segments that we're rotating are parallel to the line I'm rotating about. Okay, so let's jump into a few more examples here just to see how this works. So this next one, we need to graph that region. This is going to be a parabola that opens upside down and crosses at 1 and 3. So this is a parabola, not a circle. So this is the region I'm working with. We're rotating this about the y-axis again. So again, this is a region that would not be nice to integrate in terms of y because there's not a clear right function and a left function. So this region itself, I have to integrate in terms of x. And since I'm rotating about a line parallel to my little line segments, I'm going to use the shell method here. Okay. In any of these problems, you could potentially have a washer or shell method. So we're going to need to spend some time in class talking about, like, how do I tell? Is it shell or washer? But since we think we have a shell method here, this is going to be an integral from 0 or from of 2 pi. My bounds are going to be 1 and 3 because those are my x values on my integral. Now I need the radius and the height. Okay, so the radius again is the distance from that little line segment over to my axis of rotation. So this is going to be x to 0. So my radius is going to be x minus 0, which you could just write as x. My height is the height of that little line segment, which is just going to be my function here. Cool. So the second part of this problem is asking us now to rotate instead about the line x equals -3. X equals -3 is over here. So again, that line is parallel to my little line segment. So I'm still going to need the shell method. I'm still going to have a 2 pi out front. The 1 and 3 are just based on my region, so they're still going to be there. Now my radius is the distance from that little line segment all the way over to the line that I'm rotating about. And so in this case, my right function is x. That's just the arbitrary x value. My left function is -3. So I'm gonna have to do x minus -3, which is x plus 3. That's the length of my radius. Sometimes students struggle with the radius. So if that's confusing, let me know in class. The height is still going to stay the same because that little line segment that I'm rotating didn't change. Just its distance from the axis of rotation is the only thing that changed. So my height is still -x squared plus 4x minus 3. So this is my radius. This is my height, still in terms of x. Okay, and one last example here. So we've got the function drawn here. This is being rotated about the line y equals 5, which he lives up here. Okay. And so if I look at this region, again, this region cannot nicely be done in terms of x because there's not a clear top and bottom function. So this region itself needs to be done in terms of y. Again, the line I'm rotating about is parallel to the line that my axis of rotation. So I am going to have to use the shell method here. So we get shell method. We're going to do things in terms of y, we said. So we'll have a dy at the end. We always have the 2 pi out front from the shell method. My bounds are going to be 0 to 4 because those are the bounds on the region. The region is what dictates my bounds, not what I'm rotating about. Okay, so my radius now is the distance from here to here, from the line I'm rotating about to some arbitrary value. This is an arbitrary y value, so my radius is the distance from y equals 5 to an arbitrary y value. So this is going to be 5 minus y for my radius now. And my height is going to be sideways here. My height is this length here, because what we're thinking about in this case is that we have a sideways cylinder. So my height is that distance instead of we just think about it's on its side. So my height is just the function 4y minus y squared. Sometimes with the height, if there's like a gap in there, you might have to do right function minus left function or top function minus bottom function. In this case, we didn't have anything tricky like that, but we might see something like that in class. Okay, hopefully the shell method makes a little bit of sense to you. If not, we'll do more in class.